Today we're going to tackle a topic called resonance. Resonance is going to can be a bit confusing. So I think it's good for us to start with this. Where does the idea of resonance come from? So where did they come up with this wacky idea that is known as resonance? What data led chemists to come up with this explanation for what they're seeing? All right, so it starts with this. Experimentally, chemists find that single bonds are longer than double bonds. Double bonds are actually longer than triple bonds. So triple bonds are the shortest, and then come just double bonds, and single bonds are the longest. So when they look at a structure like benzene, okay, and so this is what benzene looks like. Benzene is C6H6. Okay, and the structure of benzene it's a ring structure. So it is 1, 2, 3, 4, 5, 6. Okay, it's a ring structure, and coming off of each carbon is a hydrogen. Now, to make this thing a little bit easier, in organic chemistry, chemists will actually write this instead as looking like this. So it would be 1, 2, 3, 4, 5, 6. 1, 2, 3. All right, so this actually represents this, where at each apex here, there is a carbon, and then coming off of that carbon is a hydrogen. And so we just make that assumption when we look at a structure like this. And the double lines here means that these are double bonds, just the same as here. Okay, so when chemists look at the structure of benzene, what they find is something very unusual. What we would expect to find is that there should be 1, 2, 3 bonds in benzene. 1, 2, 3 bonds in benzene that should be shorter than the other 3, right? Because these are single bonds and these are double bonds. Single bonds, double bonds. But is that what they find when they look at this molecule? It is not what they find. So, half of the carbon-carbon bonds should be longer than the other half. Half of them are double bonds and half of them are single bonds. But experimentally, that's not what's found. What is found is that all the carbon-carbon bonds are the same length in benzene, and that length is somewhere between the length of a single bond and a double bond. So it's not exactly as long as a single bond, but it's not exactly as short as a double bond. So then, what are chemists' best explanation for this experimental data? Well, what they say then is that the double bonds must move. They must resonate. Okay, and this is a very bizarre idea. And so this is how we draw resonating structures. Here is the benzene. 1, 2, 3. And what we do is we draw another structure. 1, 2, 3, 4, 5, 6. Okay, see the double bonds are in different places. And so what scientists say, chemists say, is that the benzene structure resonates. Okay, so the double bonds jump from here to here, 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 here to here. Okay, so that's what it means it's resonating. It's going back and forth from this structure to this structure to this structure to this structure. That's resonance. Okay, we know we've got a resonance structure when more than one Lewis structure can be drawn for something and they're both equally correct. Benzene is a very typical resonating structure that you will see a lot. The other structure that is a typical resonating structure is ozone. Okay, so that's the other example I want to make sure that we have. So this one is benzene, C6H6. Okay, the other one that's very important is ozone, O3. And the two equally valid Lewis structures that can be drawn for ozone looks like this. O, O, O. And then we've got a lone pair. We've got a couple of lone pairs. And then here we have 1, 2, 3. Okay, so what I'm going to draw, you're going to say, well, can't we just turn it around and make it look exactly like that? And no, we can't. Let's number our oxygens so that we know that it actually is different. So oxygen 1, 2, 3. So what happens in this resonating structure, believe it or not, is that not only does the double bond go back and forth, but what else goes back and forth with it too? Lone pair goes back and forth. So the other structure that's equally as valid would be this. So we've got that lone pair staying there, a couple of lone pairs here, and then okay, so this is the structure of ozone, a resonating structure. Back and forth, because like benzene, the bond lengths in ozone are identical, somewhere between the length of a single bond and double bond. Okay, that's it.